Welcome. Thank you for attending this session. My name is Brad Calder. I'm a Director of Engineering and Architect for Windows Azure Storage. Windows Azure Storage provides essential storage services for the cloud. And in this session, there'll be a lot of storage details. So if you're a storage geek like me, hopefully you'll get something out of this session. So over the last 2 days, you've heard about Windows Azure, which is the underlying foundation of Microsoft's cloud platform. You can think of it as an operating system for the cloud that provides essential services for the cloud, such as virtualized computation, scalable storage, automatic management, and a rich developer SDK. And the focus of this session is to describe to you in detail Windows Azure Storage. So this is going to allow you, the application developers, to build your applications to access the vast amount of available and reliable storage that's in the cloud. So you're going to be able to build your applications so that you can access your data efficiently from anywhere at any time, store any amount of data for any length of time, be able to be confident that the data will not be lost, and basically pay for this as a utility-based resource. So you basically only pay for what you use and store. Now, the underlying foundation of the storage system is a storage system that's durable, scalable, highly available. It has security for authenticated access, performance efficient, and we built this at Microsoft to have a lot of rich data abstractions for service communication, storing and accessing large data objects, and manipulating service state and querying over service state. And for the CTP, we're providing access to queues, blobs, and tables. And this is being provided access via a REST interface so that you can use any programming language or platform to access the storage, as well as ADO.NET. Now, before you can access these data abstractions, the first thing you need to do is to create a storage account. So you go to our website, you create a globally unique name, which is the storage account for you, and with that, you receive back a 256-bit secret key. And with that 250-bit secret key, you can create a signature for each of your requests and use that signature for each request that you create to authenticate that access to the store. So for each request, you use your secret key along with the URL and the HTTP header to create a signature. And you send that along with your storage account and the request to the blob store or table store or queue store to do the authenticated access. So what are these three concepts that we're providing via Windows Azure Storage? Well, for blobs, we provide a simple interface for storing name files along with metadata for a file. For tables, we provide access to structured storage, where a table is a set of entities, and an entity is a set of properties, and you can query over these entities and properties. And for queues, we provide reliable delivery of messages and storage of messages for applications. So I'm going to go through each of these three in detail in this session. So the three first concepts for blobs are you have your storage account, and with your storage account, you can create a container, and all your blobs actually live inside of what's called a blob container. So in this example, we have an account named Sally, and assume you're Sally and you want to create and store some pictures in the cloud. So you might create a container called pictures, and then you might do a put to put these two images into that container. Similarly, you might want to store a movie in the cloud. So you might create a movies container, then store this movie inside that container. Now let's go into these concepts in a little bit more detail. With your storage account, you can create one-to-many blob containers. Each blob container has a unique name. That name is scoped by the account. And with the container contains these set of blobs that you want to access, but you can also specify a lot of additional things at the container level. For example, you can specify sharing policies at the container level. So you can specify that all the blobs within this container should be publicly readable or private. So going back to our picture example, you might want to share your pictures with other people on the web, so you might want to make that pictures container publicly readable. Or if you don't want to share it with anybody and only make sure that you, the authenticated owner, has access to that container, you might want to make it private. And the default when you create a container is private. You can also associate metadata with a container. So these are name value pairs up to 8 KB in size. And this is useful for potentially associating information, let's say, with your picture album. You want to associate who is the photographer of the picture album, how many views were there for the picture album, etc. Okay? You can also list the blobs in the container. Now, what does the URL look like for accessing a blob in our blob store? Well, that's shown here, where the first part of URL is your storage account. You then specify the keyword blob, which indicates to us that you want to access the blob store. corewindows.net, then your blob container name. The blob container name cannot have any slashes. And then the rest of the URL is the blob name. So let's go through another example where we have the account Sally, and we want to create a container music and store music into the cloud. Now, the point of this slide here is to show that the blob namespace can actually be used as a hierarchical namespace which you can manage yourself. So in this example, we're going to create a blob namespace where we're going to use a delimiter, which is the /, and we're going to specify when we store our blobs that the first part of the namespace is the type of the music, the next part of the namespace is the band, and the last part of the namespace is the song. Then given this URL shown in yellow, you can then put this music file into the cloud and actually retrieve it from the cloud. Okay. Now, how big of blobs do we store? Well, you can store for this CTP up to 50 gigabyte blobs each. And we provide this via a standard put and get REST interface. And for every blob access that you do, you have to specify this URL that's shown here. Okay? Then for the put command, what that effectively does, or the semantics for that, is that you insert a new blob into the store, or you're effectively overriding the existing blob into the store. Then for get blob, you're actually getting the whole blob from the store or getting a given offset and length from the store. And then we support delete blob. Now, we also support efficient continuation of upload for blobs. And I'll get to that in the next slide. The other thing you can specify for a blob is name, value, metadata information, similarly to what you can do at the container level. So going back to our picture album example, you might want to actually associate with each of your pictures who's in the picture or a caption with the picture. And this is information that's easy to be stored with and retrieved via the metadata information associated with a blob. And so you can get this information and set it separately from the blob bits, and you can store up to 8 KB per blob. Now let's get to the efficient support for continuation of upload. Now for our storage system, we want to support storing tens of gigabyte sized blobs, if not hundreds of gigabytes sized blobs at some point. So we need an efficient way to upload these blobs and deal with failures if there's an issue during the upload. So if there's a failure, we don't want to have to start over from the beginning of the upload with a standard put request. And so the way we do this is we actually break our blobs up into what we call blocks. Okay? Now, assume we're a DVD service, and so we have an account named DVD. We have a container called movies, and since Halloween's right around the corner, what's the best movie we can actually upload for everybody to watch is The Blob for our blob store. Okay? It's old classic. So what we're going to do here is we're going to specify the blob name, which is scoped by our container and our account name. Then we're going to take our blob, our 10 gigabyte movie, break it up into what we call blocks. Each block has a unique name, which is scoped by the blob name. And then what you do is you put each of these blocks into the store scoped by that blob name. So each of these blocks are associated with the blob that we've actually defined. So we're going to do a put block, put each of these blocks up into the store. And if there's a failure for one of these put blocks, you can retry and then continue where you left off. Okay? Now, once you've actually put all your blocks up into the store for this blob, the next thing you do is what's called a put block list. This commits for that blob a list of blocks which are going to represent the readable version of the blob. So that's circled here in red. So this block list, in that order, will specify the readable version of that blob. And the advantage of doing this is that we get efficient continuation on retry, as well as you can even upload the blocks in parallel or out of order. Now let me dive into this in a little bit more details to show a few things. So we're going to go through an example where we have a blob called example blob. And there's three things I want to show with the example. One is uploading blocks out of order. uploading blocks with the same block ID, and uploading unused blocks, and the effects of those three scenarios. So we're going to put blocks for this blob in the following order. We're going to do a put block of block ID 1, do a put block of block ID 3, do a put block of block ID 4, do a put block of block ID 2, and then for some reason we never got an ACK back for when we did the put block of block ID 4, so let's put it again. Okay? And now for this example, I want to create a blob for example blob such that the readable version of that blob, if I read it from beginning to end, would consist of block ID 2, followed by block ID 3, followed by block ID 4. And that's what this put block list will do. So it's going to select these 3 blocks and form the following readable blob. So if you read this from the beginning to end, you'd see the block data bits for block ID 2, 3, and 4. And so what matters here in terms of uploading, you can upload your blocks out of order, but what matters is the order of the blocks in this put block list. The other part of this example is that we actually uploaded blocks with the same ID, block ID 4. Well, that's okay. The last block committed will be the block that's used for the readable version of the blob. And then we've also uploaded blocks that don't end up getting used. Ooh, sorry. Such as block ID 1 in the first upload of block ID 4. And what happens here is that when you do your put block list, these blocks become disassociated with the blob, and they're garbage collected. So what that means is that if you actually wanted to use put block ID 1 again in another put block later, you have to upload it again. Okay? So I hope that gives you an example of the details of the different semantics of uploading blocks and committing them as part of a put block list. Now let's go back to our storage concepts and add blocks to that. So what does this mean? This gives us 2 ways to upload data for blobs into our storage system. One is you can use the standard put blob request, where here we're doing a put blob of image 1 and image 2. Each of those are a single put blob request. Now, one thing I didn't say earlier, which I want to clarify now, is that for the CTP, a single put blob request can be up to 64 megabytes. Okay? So if you want to go up to 50 gigabytes for a blob, you then need to use the block interface. So with that, you can do a put block of, in this example, block ID 1, 2, and 3, then do your put block list, and this will now be the readable version of the blob called the movie. Okay? The other thing I want to point out with this slide is when you actually read your data via get blob, everything is done in terms of just the blob name. So you specify your account, container, and blob name. You actually don't specify blocks at all when you read the blob. Okay? So just a little bit more details about blocks. Actually, under the cover, all blobs are blocks. The properties of blocks are that each block is defined by a block ID, and that can be up to 64 bytes, and the block ID is scoped by the blob name. All blocks are immutable, and a block can be up to 4 megabytes. But all the blocks inside of a put block list that you actually want to commit, they don't have to be the same size. They can be different sizes. Now, there's 2 block list operations we support for the CTP. The first one I've actually already described in details with the examples, but I'll just go through those real quickly just to refresh our memories. When you do a put block list, you provide the list of the blocks, and the order of the list of the blocks with the put block list will be the readable version of the blob. If multiple blocks are uploaded with the same block ID, the last committed block wins. And if you do a put block list and there's no blocks that are, there's still blocks that were committed before you actually did the put block list, if there are blocks that were uploaded before you did the put block list, those blocks will be disassociated with the blob and GC'd. Now, if you actually did a put block list where you actually uploaded a blob, where you actually provided that list, we actually store that list with the blob in the storage system. So you can later actually retrieve it. So you can actually do a get block list and retrieve the full list of blocks you uploaded. And for each block, it lists the block ID and the block size. Okay. Now let's go through the actual REST calls for doing a put block list and put block for the movie The Blob. So we have here our account DVD, container, movies, and the blob name. So when we do our put, we specify as an additional part of the URI that we're actually doing a put block. We specify the block ID here to be block ID 1, and a timeout in 60 seconds. We then specify our HTTP header, where the content length here specifies the content length of the block in its binary form, which will be 4 megs. We also specify here a content MD5. This is a content MD5 which we check at the store. This is optional, but if you provide it, we check it at the store, and if it doesn't match what we got in terms of the block bits we see, we'll return an error to you. In addition, you pass in your signature I mentioned earlier, which you create with your secret key, a date, and then the block bits themselves. So this gives an example of uploading the first block of our movie, The Blob. Now, assume we've actually uploaded all the blocks, and the next thing we want to do is do the put block list. So here's an example of that, where for our URI, we specify that we're doing a put block list with a timeout of 120 seconds. We specify the content length of the block list, the signature for the secure authentication, time, and then the block list. Okay. Now that we've uploaded the blob into the system, and with this block list, we specified the readable version of the blob, we're going to do a get blob. Well, if we've actually specified that the movies container is publicly readable, we can actually just specify this request right here. And this will start downloading the whole blob movie. If it's secure access, well, you have to provide the secure signature and the date and time. If we actually only want to get a range of the blob, you can do that too, by actually specifying an HTTP header where you actually specify the range. And in this example, we're specifying a range of 1 megabyte to 2 megabytes, which is our favorite part of the blob movie. OK, the next part I actually want to show is treating the blob namespace as a hierarchical namespace which you can enumerate over. So assume we have all of the movies shown in the movies containers shown on your left. Okay? If you did the request shown on the right, which is a get request, on the movies container, and you specify list, this will list all the blobs shown here on the left. Now, let's say we only want to list the first part of our namespace, or the first part, the directory part of the namespace. What we'll do is we'll specify a delimiter. Here we specify our delimiter /, which we used in our namespace when we created it. And then what we get back is the following 3 items, which specify that these are blob prefixes. So this indicates that with this delimiter, we match these blob prefixes, meaning that there's blobs in our store with this prefix below the /. And you can treat these basically as directory structures if you want to. Okay? Well, let's dive farther into the drama directory or prefix. So here we're going to actually look one level down in our directory inside the drama prefix, and we're going to actually say, OK, list everything down there up to the next delimiter. And if you do that, you get the following results. We find the drama crime blob prefix, and we also find the blob drama / memento. Now, one of the points I want to make here is that the delimiter, in this example, I just used a /. It can actually be any valid blob character or even multiple characters. Okay. Now, since I put together this example, I also want to show you our continuation support for listing of blobs. So let's say you only wanted to list 3 blobs at a time. And in this example, with the get request on your right, we do a prefix where you want to list just the blobs that are action movies. So we're going to do a prefix where we also specify only list me in return 3 items. This will return the following result. It'll get you for the first 3 Rocky movies. And it also returns an opaque marker. This indicates that there's additional blobs in the system that match this query. Okay? You then can execute the same exact query again and specify a marker that you got before, and then it will return the next set of 3 results. And in this case, there was only 2 more results. And the next marker is empty. Okay? So in summary, for Windows Azure blobs, we provide an easy REST put, get, and delete interface where you can read from the whole blob, or you can read from a given offset and length for the blob. And there are some additional features I didn't have time to go into in this talk, which are pretty rich, such as conditional put and get. With conditional put, you can actually treat the blob store as a store providing optimistic concurrency. So you can conditionally put a blob based upon if nobody's actually updated that blob since you've last read it. Similarly, with conditional get, you can actually conditionally get a blob based upon if it's been modified or not, depending on what you want to use. Then in terms of the blob size, we support up to 50 gigabytes for the put block list. If you do a single put blob request for the CTP, we support up to 64 megabytes. And a big feature of this blob system is the block interface itself and the efficient continuation for uploading, especially since we want to support uploading of tens of gigabytes to even, at some point, hundreds of gigabytes blobs. Now, one point I want to make out for the semantics for our blob interface for the CTP is that the semantics is basically replace blob. You basically are inserting a new blob into the store or replacing that blob. And the reason I want to make a point of this is that some future support we're going to have is the following. We'll support update blob, append blob, and copy blob. What update blob does, it allows you to replace, add, or remove blocks within a blob. Append blob allows you to append blocks to a blob. And copy blob allows you to copy an existing blob to a new blob name in the store. Okay. So now I want to describe Windows Azure Tables, which allows you to efficiently store and query structured data in the cloud. So the goal here is to provide massively scalable tables which allow you to store billions of entities or rows and up to terabytes of data. And we built this to automatically scale your table to hundreds or thousands of storage nodes to meet your traffic needs. And the tables are highly available and durable. And they're provided with access via familiar and easy-to-use programming interfaces, and that's via the already existing Windows ADO.NET data services. So you can access the structured storage with .NET classes and query over them with LINQ, or you can use REST, where you can actually access the storage with any platform or any other language. So what is our data model for our tables? Well, within your storage account, you can create one-to-many table names, and each of these tables' names is uniquely scoped by the storage account. Excuse me. Then the data you store within the table are called entities. And each of these entities contain properties. And you can think of the entities as rows and the properties as columns. And every entity is uniquely defined by two keys, a partition key and a row key, where the partition key is used to enable the scalability of your table, and the row key is uniquely to define the entity within the partition. And let me get into that in some more detail now. So first I want to define what a partition key is and a partition. Okay, every table has to have a partition key. You can think of it as the first property or the column of your table. What we do with this is we group entities together in the table that have the same partition key into what we call table partitions. So a table partition are all the entities in your table with the same partition key value. And we expose this partition key to the users in our programming model to allow the applications to control the granularity of their partitions and to enable the scalability. So let's go through an example. So here we have a table, which is a document versioning table. And each row represents a version of a document. And the properties we have here from left to right are the document name, version, modification time of the document, and a description. Okay, so each of these properties you can think of as columns, and each of the documents here is a version of a document which you can think about as an entity, which is an entity. Now, what we do with the partition key, which is the first key shown here on the left, is we group together all the entities with the same partition key value into what we call partitions. So in this example table, we have two partitions, partition 1 and partition 2. Partition 1 are the entities for the examples document, and partition 2 are the entities for the FAQ document. Okay? So what does this give us? What does this allow us to do? Well, it gives you two things for the CTP. This is entity locality and table scalability. With entity locality, what that means is that all the entities that are grouped within the same partition are effectively stored together. This means you'll get more efficient querying over those entities because of cache locality, as well as only have to go into a single partition to get those results back. Now, you also get, via these partition key, table scalability. We basically monitor the traffic patterns of these partitions, and we scale your table out over multiple servers based upon these partitions to meet your traffic needs. So going back to our example, if we wanted to get all the versions of the FAQ document, that's quite efficient because these are in the same partition, partition 2. Okay? So we would go to that partition, retrieve the documents, and this is efficient due to entity locality. Similarly, we have also shown here 2 partitions. So if there's a lot of traffic to partition 1 and partition 2 for this table, we can actually serve these two partitions on different servers. Okay? So that's how we basically scale out the access to your overall table. Now, a common question we get here is, how do I choose my partition key? Well, you want to choose a partition key that's sort of common in your queries. Okay? Because if the partition key is used in your query, this gives you fast access to retrieve the entities within a single partition. If the partition key is not specified in the query, then that means you actually have to traverse over all the partitions to find the entities you're looking for, and that can be more expensive. So going back to our example, let's say we want to do a query where we want to get all the entities where partition key equals FAQ doc. Now this will be quite fast because we go to partition 2, we traverse over the entities there, we find the ones we're looking for, and return the results. Okay? And this is great because the partition key was part of our query. Now, if the partition key is not part of our query, so let's say we want to get all the docs modified before June 2007, this will be more expensive because we have to go to each partition, traverse over the entities, find the one that we matched this query, and return it. Okay? Now, one point I want to make here is you can query over any properties in the table. Okay? But if you actually specify the partition key as part of your query, it'll be much more faster, okay? Or much more efficient. Okay, so that's the first thing you need to think about when choosing a partition key. Now, the second thing you want to think about in choosing a partition key is scalability. Now, you want to choose a partition key that allows your data to spread out over multiple partitions, and more importantly, actually the load for your data to spread out over multiple partitions, okay? Because the more partitions you have, the easier it will be for us to automatically load balance that across the servers. Okay? And we expose the partition key to the application so that you can control what goes into your partitions. Now, there's a trade-off here between trying to get a benefit from entity locality and this scalability. At one extreme, you can put all of your entities into a single partition, okay, and get entity locality. But that doesn't allow us to scale your table out across multiple servers. At the other extreme, you could actually give each entity a unique partition key value. And this means that gives us endless possibilities to spread your partitions out over our servers to meet scalability, but you're not trying to take advantage of any of the entity locality. So those are sort of the 2 trade-offs you have to deal with. Now, the last thing I want to show with this example is the second column, which is the row key. So the 2 keys, if you remember when I started this section, is that you have to have for every entity is the partition key and the row key. The partition key identifies what partition an entity is in, and the row key is just the unique ID of the entity within that partition. Okay? So the features or functionalities for entities and properties are listed here, where each entity you define within a table can have up to 255 properties. The mandatory properties for every entity, as I mentioned, are the partition key and the row key. And we also reserve one of these properties to be a system-maintained version. And this is used to provide optimistic concurrency. Okay? Now, for the rest of the properties stored in an entity, there's no fixed schema enforced. Okay? We store them as name type value pairs. And so 2 entities in the same table can actually have different properties. And you can even have 2 properties across 2 entities in the same table with the same name, but different types. It's up to you to maintain that for your table storage. Okay? And how you actually want to define your schema and use it. Now I want to go through actually an example. Well, first, the different property types that are supported are the partition key and row key have to be of type string. The property types can be of type string, binary, bool, datetime, GUID, int, large int, or double. Okay. Now I want to go into how to actually program the tables and give some examples with ADO.NET. Okay. So we're providing access to our structured storage via ADO.NET, where you can use the link to query over your table. And REST access is also provided, which is defined via ADO.NET, to allow you to access the structured storage with any programming language or platform. Now, the type of operations you do on the structured storage is that you can insert, update, and delete entities, and you can query over the tables to retrieve back a set of entities. And with your queries, you can actually specify any of the properties as part of the query expression. Okay, in this part of the example, I'm actually going to switch to using a customer table. So I want to have a customer table and customer entities. So we want to insert customers into this table and query over them. So in using ADO.NET Data Services, the first thing I'm going to do is define my customer class. This defines the class that's used to represent the entities that I'm going to store into my table. Okay? As I mentioned, the two mandatory keys that you have to provide are the partition key and the row key. In this example, we're going to use the customer last name to represent the partition key, and we're going to use row key to represent the customer first name. Now, then you can specify additional properties that we're going to actually store in this entity. In this example, we have customer since, which is the date time. So how long has the customer been a member of our service, the rating of the customer, and the occupation of the customer. Okay? Now, to hook this into ADO.NET Data Services, there's one additional thing I need to do, which is actually specify a data service key. And this is just standard ADO.NET Data Services at work here. You have to specify an annotation for this class indicating the two keys for the class. Okay? So now we've defined our customer entity class. The next thing I need to define is the customer table. And to do this, I'm going to introduce two concepts. Okay? The first concept is the master table. So for every storage account you actually have already defined inside of it a master table. This table is used to keep track of all the tables that you create. So if you actually want to create a table, you first have to register it with this master table. And the class that's shown here is the default schema or class definition for that master table. And it's only showing one member field, which is the table name that you need to define when you add a table to this master table. In this example, we're going to add customers to this master table. Okay. The next thing you need to define is with ADO.NET Data Services is what's called a data service context. A data service context is an object that allows you to access the storage in the cloud. Okay? The first thing you specify and pass into the data service context is what's shown in red, which is your storage account table.core windows.net. And once this data object is created, you can then access the storage system accessing tables for your storage account. Okay? Now that we have the data store object to access your storage account, let's go ahead and create the table. And that's shown here. So we're going to create a new master table object specifying that we want to create table customers. Then we're going to say add object with this table object to our master tables. And this will actually register with our data store context. And then when we do save changes, this will push the update to the store in the cloud. Okay? So once we do this save changes, we have now created the customers table and registered that with our master table for our storage system. Okay? So now that we've created the customers table, let's go ahead and actually create customers that we can put into this table. And the way we do that is we use our customer class we defined earlier. And here we create a customer named Getty Lee. And what we're going to do is actually add this customer to our table. Well, the first thing we need to do this is, yet again, a data service context object, because this is our lifeline to the store for structured storage with ADO.NET services. Okay? Then the next thing we do is we're going to add to our context the customer object and specify that we want to add this customer object to the customers table. Then once we do save changes, this will push the insert to the cloud. And that's basically as easy it is to actually put inserts and add objects to the cloud for structured storage. Okay, now that we've actually put some customers into our customers table, I want to show querying over that table using LINQ. So here again, we need to have our data service context, and in this time I used a my account as the account name. And then we're going to use LINQ to query over the table. We're going to say, from the customers table, retrieve all the entities and all the properties for the entities where the partition key equals Lee. So this will retrieve all the entities that have partition key equal to Lee once we do the for each statement. So when you do the for each, that will send the query to the store, retrieve back the set of entities, and then you can enumerate over those entities. Now, I also want to give a taste of what this looks like in REST. So this is what shown here. You can actually do the same query in REST by specifying get your account name .table.core.windows.net, then the table name, in this case it's customers, and then you're going to filter on the table name, and then you're going to say, well, the query is retrieving the entities where the partition key equal to Lee. Okay? And this is basically the same thing as we did with LINQ, but with REST. Okay? The final thing I want to show is updating and deleting entities for our table. Now, we want to get the customer Getty Lee out of our store that's in the cloud that we already inserted. So we're going to do a query where we specify the partition key Lee, row key Getty. Now, we want to update a field. Let's just choose occupation. Didn't quite work out for Getty to be an engineer, so he became a musician. Once we have that updated field, we then register this customer with the context. Okay? And it's important that we're actually registering this changed customer object with the context that we actually use to do the query. Okay? This is part of ADO.NET Data Services. Then when we actually do save changes, that will actually push the change to the store. Okay? Next, you can do the exact same thing with delete, where we register this customer with the data store context we use to retrieve it, and then we say save changes, and that will actually delete this customer from our store. Now, one thing I want to point out here is when you actually do save changes for an update and delete, this actually does an optimistic concurrency check. You do have the option to turn that off, so you can do conditional updates and unconditional updates and deletes, but by default, it's a optimistic concurrency check. And I'm not going to go into details in this talk. There's an in-depth detail table talk tomorrow by Naranjan and Pablo, and it's EC07. Okay, and they'll go into those details. Okay, in summary, for Windows Azure Tables, this is built for massive scale, for high availability, for durable structured storage. And one of the key features is this partitioning, where we expose the partition key to the application developer to allow you to control the granularity of your partitions. And we scale these partitions out by automatically monitoring the traffic to the partitions and then spreading them out over the servers. Access is provided via ADO.NET Data Services. And one point I want to make here is that what we're providing here for Windows Azure Tables is not a relational database. You can do the operations I just described, where you can insert, update, delete entities. You have these rich property types for entities, and you can query over entities. But we're not providing things like joins or maintaining foreign keys or those types of operations. So the goal here is not to provide a relational database, but a scalable structured table system in the cloud. Now, there's two future features I want to talk about. One is, for the CTP, we provide the results back to you given a single index. So when you do your query, you can query over any properties and combination of properties, but when you get your results back, they're always sorted by partition key and row key. In future, we'll support secondary indices, which allow you to return results sorted by other properties. Another future feature is that what we provide for the CTP is ACID transactions for single entity insert updates and deletes. So we provide strong consistency for these insert updates and deletes for an entity. In the future, we'll be providing what we call entity groups. So this allows you to do atomic transactions over multiple entities within the same partition. So with an entity group, this will allow you to do multiple inserts, updates, deletes, or combinations of those across entities if they all have the same partition key value. And that means they're in the same partition. And so this will be coming later next year. Okay. So now I want to move on to queues, which are basically a cornerstone of Windows Azure for communicating between different roles. So if you've gone to the talks yesterday, you've probably seen this picture, where with Windows Azure, we provide you the ability to create a web role and a worker role. And the queue is a mechanism that you can use to actually queue up work between these two roles. Okay? So the queue provides reliable delivery of messages. So you can think of it as an asynchronous work dispatch between this web and worker role. And the programming semantics for queues are that we ensure that every message is processed at least once. The queues are highly available, durable, performance efficient, and REST access is provided for the queues. Okay? Now, the data model for the queues is as follows. You have your storage account, and inside the storage account, you can create queues. Each queue has a unique name, scoped by the storage account, and the queues contain messages. And there's no limit on the number of messages you can put into the queue. But for the CTP, messages that live in the queue longer than a week will be GC'd. Now, to access the queue, you use the URL shown here on the screen, where the left part is your account name, which is the first part of your host name. You then specify the queue keyword, corewindows.net, and then the queue name. Then the messages you store into the queue, they can be only up to 8 KB sized. So if you want to actually store something larger in the queue to communicate between your web role and your worker role, you can actually store those larger items in the blob store or the entity table store, and then store the names of those in the message. Now, for the functions that we support, for queues, you can create, delete, and clear queues. And you can also inspect the content length of a queue. And this is a pretty important feature. Because inspecting the content length of a queue between a web role and a worker role allows you to determine potentially how to scale your worker roles. Okay? If the queue length is empty most of the time, then that may mean that, well, maybe you can reduce the number of worker roles you have. If the queue length is full, overflowing most of the time, well, maybe you need to add a few more worker roles to keep up with the incoming work that you need to do. Okay? Then the messages that you store in the queue, we support a standard interface where you enqueue a message into a queue. But for dequeue, we have a special thing that you need to do, which helps us to ensure this property of making sure that every message is processed at least once. So when you dequeue a message, you specify the queue name and this invisibility time. Okay? What happens is that the queue will return the message with a message ID, and it will make the message invisible for that length of time. Okay? Now, if you call delete within that length of time with the message ID, that will then delete the message from the queue. If you don't call delete within that amount of time, the message will become now visible again for some other worker to actually consume that message. And let's go through an example for why this is useful. So we assume we have the following producers and consumers, where the producers are, for example, your web front-end role, and the consumers are your workers. We have the following 4 messages queued up. And the first thing we're going to do is consumer 1 is going to dequeue a message, and it gets message 1. And it's going to specify that we're going to have an invisibility time of 30 seconds. Okay? Then worker 2, C2, will dequeue a message, also specifying visibility time of 30 seconds. And note that it actually doesn't choose message 1. Message 1 was invisible, so it skips over that and it chooses message 2. The queue does. And it returns message 2 to consumer 2. Now, let's assume for the example that consumer 2 consumes message 2 and finishes processing it. And then the next thing it will do is it will do a delete queue with that message ID. And this will delete the message from the queue. Now, consumer 1 is processing message 1, but it's not yet done processing it. And before it finishes, it actually fails. C1 crashes. So what do? What we want is to provide our workers a way to continue processing messages and make sure that each of the messages are processed in completion. So within 30 seconds of the initial dequeue, that message will become visible if no one deletes it. And in this case, C1 crashed, so it's not going to delete it. So this message 1 became visible again, and then C2 can actually dequeue it and finish processing it to completion. And this is what provides the assurance that every message can be processed in entirety at least once for your workers. Now, to summarize, just a high-level top few points for Windows Azure Queues. One of the key points here is it provides this reliable message delivery between your web roles and your worker roles. With the semantics of that, all messages can be retrieved and processed at least once. There's no limit on the number of messages you can store in a queue, and the messages can be up to 8 KB in size. Now, finally, I want to discuss a few questions you might have about Windows Azure storage, such as, what are we doing around durability, availability, and scalability for your data? Now, for durability, we replicate all of your data at least 3 times. And the way we do this is we spread your replicas out over what we call fault domains and upgrade domains. And what this means is that no 2 replicas for a piece of your data are in the same fault domain or in the same upgrade domain. So if we have a fault, let's say a rack in the data center goes bad or goes down, we will serve your data for one of the 2 healthy replicas that are still accessible in one of the other domains. Similar, the same thing for upgrades. If we're doing an upgrade and we have to reboot a node, we still have the 2 other replicas that are in upgrade domains, separate upgrade domains, and that will serve your data from those to keep availability for your data. And all of this is provided right now for the CTP out of a single data center for this fault tolerance. We'll have future support for geo-distribution and geo-replication of the data, and that'll come at a later point in time. Now, all the storage we have, blobs, tables, and queues, these are all built on this replication layer. So one of the key points of this replication layer is dynamic replication. Okay? If there's ever a drive failure or a node failure, your dynamic data is dynamically re-replicated to get it back up to a healthy number of replicas. So if you had some data on a drive and it went down, you still have your 2 healthy replicas, which we re-replicate to get you back up to 3 or more healthy replicas. Similarly, we continuously scan your data for bit rot. So if a piece of your data or one of your replicas has a corruption, we will recognize that and then re-replicate from one of your healthy replicas to get you back up to 3 or more replicas. Then for availability and scalability, we provide efficient failover. We quickly identify if there's failures, and we immediately serve your data from one of your healthy replicas. For scalability, I talked about this in much detail in the table section, where we automatically load balance your hot data. We automatically monitor the usage patterns and load balance your blob containers, table partitions, and queues across our servers to meet your traffic needs. And finally, for scalability, we do caching of hot blobs, entities, and queues in our memory system. So for very hot blobs, we will cache these multiple times across our servers to meet your traffic needs. And then for entities and queues, we'll cache these and serve these directly from memory to meet your traffic needs. So in summary, for Windows Azure storage, it provides essential storage for the cloud for Windows Azure storage. And it provides a durable, scalable, highly available, security with authenticated access, performance-efficient storage. We wanted to leverage your .NET skills, so we provided REST accessible and also ADO.NET accessible access to the storage system. We provide access to rich data abstractions, such as queue, blobs, and tables for service communication, access of large data items, and service state. And I just want to summarize real quickly the overall data storage concepts with this figure here. With your storage account, you can create blob containers, which contain your blobs. You can create tables, which contain your entities. And you can create queues, which contain your messages. And then shown here are the URLs for each of these namespaces. And the keyword that occurs right after your storage account is what separates out the namespaces for these different objects. So this means that you can actually have a container called music, you could have a table called music, you could have a queue called music, all within your storage account. Okay? Now, for more information, there'll be a deep dive on Windows Azure tables in session ES07, which is Programming Cloud Storage for the Programming Tables for the Cloud by Naranjan and Pablo, and that'll be next Wednesday at 1:15. And here's some standard links for ADO.NET data services as well as Azure storage. And the last thing before I take questions is please make sure you fill out the evaluations at microsoftpdc.com. And that's all I have. For questions?
Hi, yeah, I have two questions. One on the security model. You talked about the public and private types of security. Is there a shared private security model? In other words, I give some other person access to my account, but they log in with their account, they get to my data.
Yeah, that's something that we're currently looking at providing. It's not part of the CTP, but we're looking at providing that at some level in the future. Okay.
So the other question I have has to do with trust. Everybody I'm talking to, kind of in the hallways and stuff about all this cloud is like, well, why do we trust Microsoft with our data? So, along that lines is, do we encrypt our data if we have a problem with that? Do we encrypt our data before we put it up into your tables and then pull it down and then decrypt it in our application?
Yes.
Or how do you handle it on your side? The privacy and the security of our data.
Yeah, so you own all of your data for your application. So you're full free to encrypt that data before you actually store it. Obviously, if you encrypt structured data, you can't quite query over it. But like blob data you don't want to query over, you're free to encrypt that before you store it.
Okay. So is there encryption going on inside your data services so like employees or people you hire can't maliciously get to my data?
Microsoft has its standard practices for dealing with that. I mean, we store very private data for lots of different services, and the same sort of standard practices are followed here.
Okay. All right. Thanks.
So I'm wondering what kind of performance you could expect executing a query against a large table that did not include indexes?
That does not include a partition key query?
Either of the keys, rather.
Well, it depends upon what type of application you have, the size of the data, et cetera. So,
you
can also do the queries in parallel. If you sort of know that you've partitioned this way, you can actually do multiple queries over your table in parallel.
Just for example, in your example customer table, if you had a property called phone number and you wanted to do a query by phone number that might cross many partitions and you had 10 million customers in your table.
Correct. And it really depends upon the size of the table. And if you had just a few entries, it'd be very quick, milliseconds. So it really depends on the size of your table. And so one thing just to state with that is, hopefully everybody here gets access to the storage system. And I do encourage you to, for the applications you're looking at providing, you can go play with it and sort of see what you get. Oh, over here, yes.
Okay, I have a question. I'm a little unclear on the difference between SQL data services and Azure tables. And is SQL data services underneath Azure tables, or are they side by side? Some of the stuff looks similar, the names are different. Can you explain why I might use one or the other?
Okay.
Thanks.
Good question. So our storage system for Windows Azure tables is built for massive scale, low cost. And as I stated in that one slide, it's not a relational database. Okay? So we're not going to support things like joins or maintenance of foreign keys. So if you need a full database type of functionality, you should use SQL services. Okay? And that's sort of a difference. SQL services is there to provide sort of the premium offer with with relational database capabilities over time. There's sort of an analogy to like Windows and SQL. Windows provides storage, and then SQL provides additional services on top of that. So if you need those additional capabilities, SQL services would be for you. If you don't, and you're just focused on these very simple tables that massively scale, then Azure tables would be for you. Okay.
I wanted to ask a general question about what kind of performance we could expect out of blobs, let's say. streaming, a 10 meg file. Are there any kind of metrics you could have there on what sort of access time there would be, and sort of, I have some experience with this where there's, if you're getting a large amount of data and you're doing it with get, breaking it into blocks, that the latency of those transactions can really impact the performance at which you're able to get them. So you mentioned that you can do these things in parallel, and I just sort of was wondering what guidance there might be in terms of, hey, I want to get a huge amount of data very quickly. I need it in some sort of order, buffered. Are there any examples on that sort of stuff or things you can share?
Yeah, well,
basically, what I want to know, is it wicked fast? I'm from Boston, so that's what we'd ask.
Yes. Well, it's designed to be fast. So again here so you can look at basically retrieving data versus uploading data.
Right.
So is your question for both or one? Or?
Well, I guess both. I mean, like I have an example here. I used to do, before I joined Microsoft, I was doing some consulting for a couple of companies, and they moved CDs around and DVDs, but 600 meg pieces of data. And it was very difficult to move these things, from Japan to the United States using a REST interface where, put a block and wait for an ACK, put a block, wait for an ACK, because the latency of these transactions just killed the performance. Yeah. So we wound up using another company's technology that used UDP and a side channel of TCP to sort of, control the flow and retransmission, and you just blast packets, blocks up.
Yep.
And so I have so when you want to perform at that level, I'm just wondering how you guys...
Well, I mean, it's a very similar concept in that you can actually put multiple blocks in parallel up. And it's really, the commit order. So
right.
The interface is built to actually provide that sort of parallelism.
Are those puts blocking? I mean, do you wait for an ACK from them, or you just... No, you just put.
Yep.
And how do you find out if it worked or it didn't work?
Well, I mean, from the client's perspective or the application,
yeah.
I may not understand that last part of your question, but you are waiting for an ACK where that was put, but you can asynchronously put.
Right. So you start a whole bunch of workers going.
Yep.
Yeah,
Yep.
Okay. So you could do a similar kind of thing only over TCP.
Correct. Yep.
Excellent. Thank you.
Okay, thanks.
So as I understand it, you can allocate more capacity to blobs and tables by some kind of magic. But what kind of metrics do you look for when you do that? And how long does it take to allocate more computing capacity?
Well, the magic is underneath the system, we monitor these partitions, and we sort of know, sort of the load to those partitions as well as the load to our servers.
But does load mean I/O? Does load mean throughput? Or
we monitor tons of things, many things, so from the traffic to the CPU usage, et cetera. So we have algorithms which we use to say, okay, for this server that is serving these partitions, there's a spike on too much load that this can handle. So right now for the CTP, within 10 minutes, we will move load off that to another server.
Multiple copies, or just another server dedicated to that blob?
We will balance it out across the servers to make sure that that partition that we moved, or however we move things, is getting enough bandwidth, or basically throughput, to meet its traffic needs.
Does that affect my pricing? Does that go up based on how hot my application is running?
Well, the pricing hasn't been defined exactly yet. That'll be with the commercial availability. So I don't know. I don't think we're expecting to do that, but...
But just in general terms, I pay more if I hit your servers harder, or is it all you can eat?
In general, you pay more in the sense that, if we charge based upon how much data you transfer, et cetera, and how much data you traverse over, you would be paying more just from that perspective.
All right, thank you.
Okay. You mentioned in there that you do auto MD5 checks on blocks. Do you also do that on block lists and smaller blobs?
Yeah, so when you do the put block list, you have an MD5. You can specify, I don't know if I included an example, and et cetera.
Great. Thanks.
Two questions for you. First, about put block or put block list. Is that the trigger to tell the GC that it can go collect unused blocks? I mean, I'm thinking about, I want to put a 50 gig set of blocks up there, and at what point does the GC say, well, this block isn't in the list yet, so do I throw it away, even though I haven't had time to put the list yet?
Yeah, so when you do a put block list, the one example I gave is anything that wasn't used in the list, that's a clear sign to immediately that can be GC'd. Now, there's another concept which is, okay, you could lazily put these blocks up in there forever, let's say. So I think for the CTP, we allow blocks that have not been put as part of a put block list to live for about 2 weeks. So if you put a block and you have not actually committed it as part of a put block list, we will GC it after 2 weeks.
After 2 weeks after it was put, so it doesn't just run every. Okay, that's good. So queues, is there an implied guaranteed order in the asynchronous queues?
So in terms of like a strict FIFO order, yeah, I guess I should have mentioned that. Yeah, there is no strict guaranteed ordering with the queue.
So even if we don't, even if we process everything out of the queue, a consumer processes every one and does and returns, deletes it within the time frame that it establishes, there's still no guarantee that there'll be any particular order between any two messages.
No, I mean we actually approximate a FIFO. It's not, but not guaranteed. Okay. And that's another good point there is that, you know, when you're using a queue and you actually do want to have an exact FIFO type of ordering, it's good to build your application so that the messages have like sequence numbers in them, so you can sort of figure out the sequence yourself.
Okay, you have a queue and you have that list of items, and you hand the first queue item to client 1, and it's running for like 30 seconds, and it passes the invisibility time. So it reappears on the queue over there, but client 1 isn't dead yet. It's actually still running. It just hit congestion. Yep. Meanwhile, we have client 2 that just picked up the first queue item because it reappeared on the list. What happens if client 1 comes back later and goes, I completed this information, now I want to delete it off the list?
Yeah, with the CTP, that's not supported, but we're looking to support that for commercial offering, but we have to see. Okay. Yep. So that won't result in an error or anything like that? It won't lock you out? Or no, you'll get back, if you try to delete it, you'll get back an error that you can't delete it. I can't remember the
You no longer have an open socket or whatever to this queue item?
No.
Okay.
Yep.
All right, thanks.
SQL Server 2005 has Service Broker. Is that what you guys are using on the back end in the cloud? Because several of the things you've described, like queues and replication, have pretty much mirrored functionality in SQL Server. So in the cloud, what are you using? Are you using SQL Server and kind of dumbing it down to provide this, or did you spin your own WCF code to do this, or what?
Yeah, I think somebody asked a question earlier and I didn't quite finish the full answer. So this is the whole stack here, from the blobs, tables, and queues, and our replication layer is all built from scratch for the cloud over the last several years.
Okay.
So this is all no SQL whatsoever. It's all built from scratch to scale for the cloud. And some of the components here are used internally instead of Microsoft services, et cetera.
Okay, thank you.
Hi, could you talk a little bit about your durability model? And specifically, you mentioned things about fault zones, and could you be a little bit more specific on what those are? Because I noticed it's all in one data center, so are you still susceptible to data center disasters or things like that could lose data?
Yeah, so the Microsoft data centers are built to be highly reliable, and they actually have a lot of redundancy within that data center. These are the same data centers we use to run all of our services. As I mentioned, future features that will be coming are geo-distribution and geo-replication, which will help address some of that. That's about all I can say at this time.
Okay, so fault zones or whatever you talked about today, what do you mean by those? Are they just different pieces of hardware? Is that largely what that is?
Yeah, that's all I can say at this time.
Okay.
Question over here?
Yeah, for the CTP, when I'm developing this, can I store files on my local machine, or does that always have to go out to the cloud?
You're talking about like if you're using the...
Yeah, I'm thinking if I'm just developing on my machine, I'm on a plane, I'm on a train, I've not necessarily got an internet connection, I'm writing some code, I'm cutting some code. Obviously, I want to store it in the cloud and simulate the environment. Can I do that on my local machine, or have I got to be connected to the cloud too?
So you can use that on the local machine with the developer SDK that we provide.
Yeah, cool.
The developer SDK that we provide runs just locally on your machine, allows you to simulate the environment for the blobs, tables, and queues, as well as our Fabric compute side.
Excellent. Thanks very much.
When I pull a message off the queue, can I tell if it's been pulled off before, if it was invisible for a time?
Not at this time.
Okay. Can you put that in as a feature request?
Sure. And if people are, go to our forums, please go to the forums and put feature requests in there and whatnot. Yep, definitely.
255 properties from entities seems to be arbitrary. Can you explain why you have 255?
Well, from our tuning of the table system, this provided a reasonable number of properties based upon the entity size we support. So, in looking at the size of the properties. So right now, there's another limitation for the CTB, which I didn't describe, which is your entity can have at most 1 megabyte of data stored into it.
Is it something like a record length or a page size for your tables?
No, that's not exactly the reason, but yeah. Okay.
Thanks.
Hi, with CTP, my data is there in the Azure tables and Azure blobs. When can we see the support for the snapshotting and versioning of this data which is sitting on the cloud?
You say you work with snapshot support?
Snapshot support. Basically, there is one version of the blob sitting on the cloud. How can I get multiple versions of the same data across?
Yeah, the one feature we're looking at is to provide versioning. That the exact date and time frame is not defined yet.
Do you have the ability to enumerate over the messages in the queue, or is that something you guys are going to be working on in the future?
You can peek at the top of the queue, but you cannot enumerate over the messages at this time.
Gotcha. Does the public ACL enable unauthenticated access, or is it just authenticated access by any Azure user?
The public ACL on the containers allows anybody who knows the URLs to access and download those blobs.
Okay, cool. Thanks.
In your examples, you used HTTP in each case. Do you also support HTTPS?
Yes, we support HTTPS and HTTP. So if you want full security, if you want security for your whole blob packet, it's good to use HTTPS.
And that's for queues and tables as well?
Yes. Okay. Yep. Good point.
You mentioned that with the tables in the future we would be able to get different sorting orders or sort by other properties.
Yeah. So
will that also mean that they will be indexed so that the performance will be good when we filter on those properties?
Yeah. So future support will be provided via secondary indexes. And when you have that, it'll be efficiently able to retrieve the data sorted by those indexes.
So I have two questions for you. The first one is around destruction. What is your story around destructing data in the blob? So if I delete something, how do you guarantee it's deleted off the disk?
When you delete it, we will garbage collect it in approximately 2 weeks.
But is there any guaranteed destruction? So if somebody were to grab the hard drive, they wouldn't have access to the data on it or anything like that?
We don't have guaranteed destruction at this time, if that's what you're asking.
Okay. And the second question is around the total amount of storage. So is there any limit? I saw there's 50 gigabytes per blob, but can we store 100 terabytes up there if we want? Or how much data can be stored?
Yeah, so we're actually building out our data centers, and so that it's to support whatever capacity that you want to actually put up there. And for a given blob, there's actually really no underlying limit on the size of a blob per se, because blobs that we store can actually span multiple storage nodes. But right now at the CTB, we only provide access for storing 50 gigabyte blobs.
Okay, thank you.
Okay.
Can you talk about more about authentication and authorization? Is public and sending the secret key that we get in our email, is that the...
So you don't send any secret key, but you use the secret key you get when you sign up for your storage account to generate a signature based upon the REST header as well as the URL and the time date. So use your secret key along with that information to create a signature. Then you pass with your URL and your REST header that signature with your request, and then we know your account name, so we actually verify that on our storage side.
Are there any plans to go to something better than that?
We've been looking at providing richer identity and authentication semantics with, you can think of other types of things out there that Microsoft supports. The exact timeline or data that hasn't been decided.
Okay. This is actually a follow-up on the authentication. So is there any plan for digest or basic auth? That's the first question. And the other is, you mentioned that you can support HTTPS. Can you force HTTPS, or is it just an option?
So you want to force your
In other words,
application to use
yeah,
HTTPS?
you could only access my objects if you used HTTPS. If you used HTTP, you'd get an error.
I see.
Is that possible right now?
That's not an option at this
Okay.
time. That's an interesting idea. For your first question, you wanted to know about
Basic auth and digest auth, standard HTTP authentication patterns, other than this custom signature key.
yeah, right now it's just the custom signature key, and we're looking at in the future what sort of authentication as well as what sort of ACLs sharing that we want to support.
Okay, thank you.
Would I be able to use the storage service to replace my hosting account? For example, could I put a domain name or use my own domain name in the URL?
Yeah, so you might call that like virtual hosting or CNAMEs and those types of things. So that's a concept that we've been looking at providing. We don't provide it at the CPT. There have been people asking for that, so it's, that's something that we're looking at.
And default document on the root directory? Do you need to specify the file name that you're retrieving in order to get it, instead of just the directory name and get the default document that's associated with that directory?
Well, since we actually don't support that at this time, yeah, that's not applicable. But I think when we actually if we do support that, I can't say yet how that will be specified.
One more question. Amazon has their EC2 service that is able to pull data from their storage service. Does Microsoft have anything like a virtual machine that can load information from the storage cloud?
So you're talking about actually, well, I think for Windows Azure, your VHDs are put into the blob store and actually loaded from there to actually run your service. Are you talking about actually storing data in a VM instance in Windows Azure and having that durable?
Being able to connect to, I guess inside the VMD, connect to and retrieve files, load files inside the VMD? Yeah,
I guess I'm not understanding. So, one thing we are considering is you can imagine having your VM node and you're writing just Windows, Server 2008, APIs, and having that sort of snapshot and backed up into the blob store.
Okay, thanks.
That's something we're thinking about.
Hi, the uncommitted blocks. Let's say it's to be garbage collected. So the next time I'm trying to put more new block, would that be any kind of a name collision?
So you upload, let's say, block 1.
Right.
And
it's not uncommitted, so it's still waiting to be garbage collected. So let's say that identity is B1, right? So next time, after a couple of days, I'm trying to put a new block, right? Knowingly or unknowingly, I'm putting the same name, B1. Would that be a name collision?
No. So as one thing I want to try to show in one of the examples, that if you actually upload the same block ID, it's the last block uploaded with the ID that will be used as the next part of the next flip block list. So it's not necessarily, it's not considered a name collision. We just basically ignore the prior block with that name.
What about, let's say, concurrency issue? Let's say multiple applications are trying to write into that, right? Yep. App 1 is putting B1, and App 2 also, for the sake of discussion, again, it puts a B1.
Yeah, so if you do concurrent updates, one of the things that some of the current customers do is they actually create a hash of the block contents and use that as the block ID. And so
that provides a uniqueness, right?
Yeah, so this gives you the uniqueness as you're coming up. And even sort of gives you sort of single instancing effects too.
Okay. The second question is, you talked about ADO.NET and REST interface for interacting with this one. Is there any kind of a SOAP support and SOAP is
yeah,
supported?
Not at this time. We'll see what additional interfaces we support, but that's not part of the CTP.
All right. Okay. Thanks.
Sure. Okay. Thanks.